Okay, so you see this from the last class. It is just a revision that we saw how to define a language. To define a language by let me just trying to fix this so I can see that if someone is writing. So guys, I have one request. Please do not chat or if because sometimes it is hard for me to read the chat. So whenever you have any questions, so please talk because I am not reading the chat. And if someone does not have mic and he write or she writes, so please anyone else who has mic and you can see that, please let me know that someone has a question. Okay, because for me it is hard to see the chat also. So now, the last time we saw that one way to define the language is just write all possible words of that language. If language is infinite, so then start writing from this very small word and then generate the next word and the next and the next big word, and then show the pattern that how you are getting these words and then put dot dot dot. So this is the first way of defining the language. The second way to define the language is this algebraic way of defining the language. Okay, so you can define your language in this way. And the third way to define the language is in form of English letter. So you can define the language in form of English sentences. So we saw three language last time. Okay, but still we feel that this is not a very complete way. We need some more language, more compact way, more concise way, more efficient way. So now we will define the language. So now this is another way of defining the language today we will see, that is called the recursive way of definition. Okay, so this is recursive definition. Um, it is exactly the same recursion which you learn in your C++ or data structure course. If you revise that, what is recursion there, so then you know, I expect that you know this information, that recursion means that it is used to break one big problem into small problem, some big problem which is not possible to solve. So we break that problem into, so first we solve the small problem, and then we, from that small problem, we find solve a little bit bigger problem, and then a little bit bigger problem, and then a little bit bigger problem, and finally, gradually, by solving small problems, all these small problems, we solve the one big problem. So that is the idea for the recursion. And recursion has a base case. So base case is something for which you do not need to solve it. It is some basic facts which you establish, and you know that. So and then from that base case you generate the next words, or the next thing of the next solution of the actual problem. And then so you must use base case to generate the next problems. It's not that, so whatever the base case you generate, you cannot, when you solve the big problem, you should not come with any other solution with that. So whatever the base case you generate, so only use that base case. You may have more than one base cases, you know, that you can write if condition, else if else part, and you may have more than one base cases, but that will be the base case. So now exactly we borrow the same concept and we derive the way to define the language. So we are saying that this is a new method to define the language. It follow this template. These are three steps, but each step may be repeated itself multiple times. But these are the, if you follow the template, so template says that recursive definition will have only three steps. Okay, what are those three steps? First step, specify the basic words, base case. First you need to figure out what is the base case, what is the basic building block, what are the uh, alphabets. So then once you figure out that, then you need to understand rules for constructing new words from ones already known. So now use the base case and derive the rules to generate the new words. So you said that 1, 2, 3, 4 are my A or B is my, let's say, part of my language. So this is your base case, and then you are saying every word will generate from A or B, but in a way that uh, it will start from A and it can have as many B's after that. So whatever the rules and restrictions you want to generate, so you need to create those rules and restrictions in the second case. And then there must be third rule, which will state that to generate any word of this language, you only use rule 1 and rule 2. There are no other rules which will help you or which you can use to generate a word which belong to this language. So what does it mean? The way you define your base case, the way you generate your rules for construction of your language, so it should be so concise, so compact that they will, by using those rules and restrictions and the base case, you should be able to generate all possible words of that language. That's the idea behind that. Okay. Any confusion here? Why, how we do that? We will see examples, but if you have any confusion, so please let me know. So then I will explain that. Otherwise, we are good. Okay, so now we are saying that this is good. Let's see one example here. Even is the set of all whole numbers divisible by 2. So we have English description of the language. This is your English description of the language. Okay, and then you, what is this language? You are saying even is a language, and it will be set of all whole numbers divisible by 2. So you are saying that my language will have all whole numbers. It will not have any fraction or decimal parts, all whole numbers, and all those numbers should be divided by 2. So this is what we came with the idea for the English description of the language. Okay, so how I ask you a question, I will give you the English description of the language and will ask you, can you please write the recursive definition of this language? Can you define this language in recursive definitions? So something like that. Okay, and then algebraic description of the algebraic definition way of defining this language. We are saying that this is another way to define the language. We are saying n can be any number. You can see that n is equal to start from 1, 2, 3, 4, and dot dot dot, and n can be multiplied by 2. So n must be multiply by 2. So what, and n can be anything, 1, 2, 3, 4. So you see that if you multiply by 2, you will get um, all even numbers. So this is second way of defining the language. But now we are interested to find the recursive definition of that. So now we are saying, okay, our base case is without any proof or any implementation, we just follow the fact. And what is that? 2 is in my language even. So I do not know what is even language. So I just write even language, and I am saying I want to generate a word. And my base case says 2 is part of my language. 2 is in even. So this is my even language. And from the base case, I generate one word of my language, and which is even. And now I'm saying if x is in even, so x is a variable, it will show you any existing number which you already generated, and at this time this number is in your language. So now what should be x here? If I see this, if you see my screen, even is equal to bracket start 2. I, from the base case, I generate only one word, 2. And now I'm saying if x is in even, and x is any existing number which I prove that this is even and this is part of my language. So what is x here in my case? Anyone?
Wouldn't x currently be 2 then?
Exactly, perfect. So at this time, because I only have one letter, one word in my language, so now my x is this. This is my x. Okay. So I am so now I'm saying if x is in even, whatever the x it will be, add 2 into that, that is also part of the even. So we follow this rule, and I have only x is 2, so I'm saying 2 plus 2 is equal to 4. So now I have 2 and 4 there. So I'm saying now I again use this rule. I'm saying I use this 4 as x now, and x plus 2 is equal to 6. So now I again use the same rule x. So now 6 is my x, because all these are x now. 2, 4, 6 are part of the even. So now if you see this, if x is in even, so now 2 is also x, y is also 4 is also x, 6 is also x. But if you again use 2 and put in this rule, you will get 4 again. So there is no need to generate the duplicate terms. So if you choose 4 as an x and put plus 2 there, you will get 6. So you already have 6 there. So there is no need to generate again the duplicate term. So we will consider that x that is that will give you a new number. So 6 plus 2, 8. 8 plus 2, 10. So this way we generate our language, and you see that just by using these two rules, I can generate any even number of my language, any even number, and it is infinite. And the third rule is there is no other rule than rule 1 and 2 to generate the even numbers. So this is this, and you must write this rule there. So whenever I ask you this kind of question, you should write the base case and then the rules, and then the third rule which must be there, that there is no other rule than rule 1 and rule 2. Okay, if it is not there, your answer will not be correct. Any question here about how we generate this recursive definition of this language? This is very simple. It's not complicated. It's pretty simple. If you understand this, that's it. This is this chapter. Now we will see some more examples, and we will figure out that uh, what are the best practices of using that, and what are the different scenarios, how we generate some more languages, and that's it. So now I go to the next slide. The next slide says that exactly what I did there. I wrote here. So divisible by 2, 14 over 2 is equal to 7. So we just have this definition. So I try to generate. First I generate that by this method. So divisible by anything divisible by 2, you see 14 over. So I want. So what is the question? Question is this: is 14 is in even or not? So I need to prove that this 14 is part of this language. Now if I follow the first method, which is the English description of the method, it says that the whole number it should be divisible by 2, then it is an even. So 14, if I divide that 2, I will get a whole number 7. Okay, this is good. It means 14 is part of the even. So I can prove that by English description of the language. Now let's see the algebraic description. It says if you multiply this number with 2, and this will also be an even language. So now I find that if you have n is equal to 7 and multiply that with 2, you will get 14. So then this will be, by this method we prove that our that this 14 is part of the language. And now the way I did the way we define in the recursive definition. So these are the rules. So now apply that and see if you are able to generate all possible words. So rule 1, 2 is part of the even. Rule 2, just x is equal to and add that, and this will be part of the even, and you generate reach to 14, and you see that with all these transitions, this transition, so 1, 2, 3, 4, 5, 6, 7 number transition. So you reach to the 14 and you prove that 14 is part of the even, and this is good. This number is part of this thing, and this is good thing. Okay, so this is very simple. It's not hard. So now we might able to improve our rules. So this is very basic definition of the of writing the rules. So but you see that this is very basic. It is not wrong, but exactly the way if you write a program, let's say someone I will ask you to write 1 to 10 on the or 1 to 100 on the screen. So everybody came with different ideas to write a program of that. So someone will just print 100 times 1 to 200 on the screen, and other person might be more intelligent and they write the simple loop, for loop, and in few lines you can print on the screen 1 to 100. So it depends on the exactly the way you can write more nice programming. The same way we have this opportunity to write more nice way of writing the rules, which will require less transitions to reach to the ultimate uh, word to prove that this is part of this language. So now we can see that this is another definition here, alternate definition to define the even language. So we are saying 2 is in even, and this is our base case. And if x and y are in even, so now if you see this, and then x plus y is in even, and then I should write here rule 3. There is no rule other than rule 1 and rule 2 to generate even language. Okay, it must be there. Otherwise, your answer is wrong. So now let's see this. So 2 is in even. So we derive our set even, and 2 is in even. So now we are saying if x and y are in even, so then x plus y is in even. So now how if you see that at this time only I have one word in my language, which is 2. So I can use this word as x, and also I will reuse this word as y. So now if I follow that, so now if you see this second step, so x is equal to 2, y is equal to 2, and according to the rules, if you add these two, this will also be an even. So 2 plus 2, 4 is an even. So what we are trying to do, we are trying to prove that 14 is part of this language, is member of this language. Okay. So then we have now two words here, 2 and 4. And now we use these two words more intelligent way. So we are using x is equal to 4 and y is equal to 4. So we use y 4 as 2 times, and we generate 8 here, and then we get this thing. So then we use x is equal to 4 and y is equal to 2. So anything which is part of my my language, so that can be x and that can be y. Okay, so you cannot use anything out of the language. So whatever you generating, so use that as an x and y. So now I am saying x is equal to 4 and y is equal to 2. So I generate 6 and I have this thing. And now I am saying x is equal to 6 and y is equal to 8. So I use this and this, and now I use 14. I understand we do not create all possible even language here in sequence, but we are not we are this is not our job at this time. At this time we just want to generate 14 by using these rules, and we successfully generate 14 here, and we prove that by these rules we can generate 14, and 14 is part of this language. So this is, so now if you see this, this definition also has ability to define any possible word which belongs to this language by using these rules, but it is more efficient way. So last time if you see that to generate 14 we performed 7 iterations, and this time we just did in 1, 2, 3, 4, and fifth iteration we perform we find the final answer. So this is a more intelligent way of defining the even language. Any question here? You guys are with me at this time and you understand what's going on, yes?
Yes, sir.
Yes, sir.
great. Thank you very much. Most of the time people have questions, but you guys do not have questions. So two things, either I am explaining very well or you guys understand very well. So let's be positive and we assume that both things are good. So let's go to the next slide. And now we have this thing here. It says that how we define um the polynomial, and we say that this is polynomial. So now we are saying that a polynomial is a finite sum of terms, each of which is of the form a real number times a power of x, that may be x raised to power 0 is equal to 1. So this is one formal definition of polynomial. Oh, sorry. And then we just try to, so now we try to define this, and then we will find some problems, that what are the mistakes we might do when we define any language in recursive way of definition. So what are the possible errors or mistakes we can do? So now let's say we at this time we want to figure out that how we define the recursive definition for the polynomial. So now we are saying rule one, x is in positive. Okay. If x and y are in positives, then so are x plus y and xy are in positive. So is this positive or polynomial? Yeah, so it is at this time we are defining the positive. So now, so there is no, so now if you see this, you are saying x is in positive. And if x and y are in positive, then so are x plus y and xy. So what is x? We start the base case with the variable. And this is, so now we do not have any concrete thing, whereas base case should be a concrete thing. Otherwise, you are not able to generate any new word. So now, if you see the previous language, if we say that x is in even, and then we are saying if x and y are in even, then x plus y is in even. So what is x? We have no idea. X can be 3. Is 3 in even? So we can assume x can be anything. So this is wrong thing. Base case should be concrete. It should be something which is part of the language, and you can write that without any proof. So now here is this mistake, that you are using x, which is abstract information. It is not concrete information, and this is violation of the of this recursive way of definition. Okay, now this is a problem here. And let's see the another way. So this is another definition. We are saying rule one, if x is in integers, is a dot point is a decimal point, and y is any finite strings of digits, even one that starts with some zeros, then x dot y is in positive. We don't care this rule is right or wrong. It does not match the template of recursive definition. Recursive definition has a template that when you define the rules, it should have three rules. Base case, first rule, how and declare the rules to generate the next words from the base case, rule 2. Rule 3, there are no other rules than rule 1 and rule 2 to generate this language. So it does not follow the template. So this is not good. Okay. So it has a, beside it has some other problems also. You can see this detail here. It is written. Okay. So it does not follow the template of recursive definition. Now let's see that this is another way. So now we solve first problem, that rule 1 become concrete, 1 is in positive, and now we are saying if x and y are in positive, so then so are x plus y, x cross y, and x division divided by. So partially this is good, but it does not cover the whole positive real numbers. It does not cover the decimal points there. It does not cover the any fractional part which is real of the positive numbers. So now this cover this match the template and assume that there must be rule 3 is written here. Okay. So assume that rule 3 is there. So now it matches the template. we solved the first problem that the rule one is should be concrete. It is concrete, but and then we solve the problem. We generate the rule two, which is the base on the base case, and you can generate that some more words. But it does not cover the all positive real numbers. So by using this definition, recursive definition, you can generate some numbers of positive set, but you are not able to generate all possible numbers of positive set. Okay, so it is not complete and compact definition. So these are some issues. I am just trying to explain that what are the possible mistakes you will do, and you need to understand when you write the recursive definition that it should cover all possible uh, words of that language. And then we are saying that polynomial. So now all numbers are in polynomial. So this is the complete definition. So we are saying all numbers are in polynomial. The variable x is in polynomial. So when we say all numbers, so the mathematical definition of number is 0 to 9. Okay, so numbers mean 0 to 9. So all numbers are in polynomial. This is my base case, and I told you you may have more than one base cases. You can have, like, if you write a code in that, you can use else condition for that. So if else. So now the variable x is in polynomial. So now if you see this, these two are my base cases. And now I'm saying if P and Q are in polynomial, then so are P plus Q, P minus Q, and the parentheses around that, and P dot Q are also in polynomial. So these are the second rule, which is here, which is third rule. But actually, if you see the template, so this match the second rule of the template where you have the rules, and then the only element that the third rule, which is fourth here, but according to the template, the third one, the only elements in polynomial are the ones that are constructed by the following rules 1, 2, and rule 3. So that's it. So now we have the complete definition of the polynomial, and by that we can generate any possible uh, term of polynomial. Okay, so this is complete definition. Are we good? So I mean, if you guys have any questions, so please don't hesitate to ask me. And then let's prove that we have this equation here, and we want to prove this, that this equation is in polynomial. And we will see that if in the previous slides the rules which we generated help us to prove that is in polynomial. Okay, so now we are, so by the first rule we are saying 5 is, so now you look at this, and what is the first rule? All numbers are in polynomial. By rule 1 you are saying 5 is in polynomial. By rule 2, you are saying x is in polynomial. X. So now rule 3, if you see this in the rule 3, uh, if P and Q are in polynomial, then you can concatenate them. PQ are also in polynomial. So P and Q are any existing number in the polynomial. And now if you see this, we have two numbers here, 5 and x. One is my P, one is my Q. So I use that and I concatenate that. The 5 and x is in polynomial. Okay. And then I am saying that another x is also in polynomial. So look at this one. So I done this. Another x is also in polynomial. So now I add another x, and this is my P, this is my Q, and then I by this is also in polynomial, and by using rule 3 where you concatenate P and Q, so you are saying concatenate that, and it means that this is 5xx, which is 5x square, is in polynomial. Okay, so this way you add another another x there, 5x cube in polynomial, and finally we generate 5x cube in polynomial. Okay, so if you see that we just follow the rules, and I mention here which rules we are following, and we generate 5x cube. We follow the same step for the next term. 8 is in the polynomial, x is in polynomial, combine that by rule 3, 8x is in polynomial, and we have two terms now in polynomial. And now we are saying this is my p, this is my q, and look at this, p minus q is also in polynomial, because we saw that it is a minus sign, so I put minus here, and p and q is in my polynomial. And then I am using another term by rule 1, all numbers are in polynomial, so 7 is there in polynomial. Okay, and then this is my p, this is my q, and it says that p plus q is also in polynomial. Okay, so I use this term and I put plus here, and I see that this is into polynomial. And now I completely got my equation back, and I generate this equation by using all the rules of my recursive definition of polynomial, and it gives, I can generate any term with that, any equation with that. Make sense? Did you guys understanding this?
Professor, your microphone is doing the thing it was doing again.
Let me move my machine a little far. So now is it good? Now my mic is good?
No, still sounds the same to me.
It's just very loud. Yeah.
I don't understand, right? I didn't do anything. If you see my setup, I am sitting in the chair and in the laptop. And it has a built-in mic. And I can listen to you very well, but again, might be my cell phone. I'm going my cell phone far. And
I can't understand anything you're saying, Professor.
okay, let me try to come close. Let's see if coming close will solve the problem. So is it good now? Is it good? So do you guys have
No, it's still bad.
that? So my understanding is somehow there's a patch come during the lecture that mic goes bad. It will come, it will recover automatically. I didn't get anything last time. My understanding was I was very close to the computer and then I go far, but and then it was okay after that, but I don't know. Let me see if I can. Those things. Okay, where is my mic here? So is it good now? So do you guys understand?
No, it's still the same as before.
I don't know. So let me go for
Are you too close again?
No, I am standing at this time very far from my computer actually. So it's still bad? Okay, now
Yeah, it's still bad. I don't know why.
so now I am almost 10 foot far from my machine, even I don't see what's going on in my screen. Is it good?
It's still something that it's hard to understand.
Okay, let's move to some other place. Okay, I'm coming on some other place now. Let's see my feed will have. So is it good now? Even far cannot be heard since.
Oh, it's still staticky.
So you were saying, so what you guys hear? So what is the noise coming or what?
It's just very loud, almost as if the whole thing got like really bass boosted for some reason.
Bass boosted. You are underwater. Okay, so I don't know how I will fix this. Okay, so let's see. Okay, audio and video connections. Use this is my speaker and this is my mic. My mic is the disconnect audio.
Do you hear now?
That sounds much better, yeah.
A lot better.
Okay. I got it. So now what, I mean, I don't know what, I didn't get it, what's going on, but I understand that if that is the case, so I should disconnect my mic and reconnect that. Somehow it get it get problem and I didn't did anything. I just disconnect and connect. That's it. What I did. Anyways, so problem is solved. So we were here. Uh, so do you guys understand? I did this polynomial and I tried to prove that this equation, which is part of the polynomial in the in this by using all these rules which we define here, and then we figure out that yes, we are able to generate. So do you do you guys understand this slide when I did? So where I generate whole things.
Yes.
Okay, that's great. Okay, so now let me get my what is going on. If mic is good, so let me go back to my original place so I can see it. Okay, so we are good here. So now we are saying, so that's it. So now there is no more new information in this. And you are saying for the factorial, you already saw this there, that rule 1 is equal to 0 factorial is part of the 1, n factorial is equal to n into n minus 1 factorial. So this is one way of defining the factorial. And then for the summation, you are saying that x is part of your summation. If w is, so now how we write the recursive definition for the summation. So we are saying for summation plus, we are saying that x is part of the summation because summation is equal to x. This is given. And then w is any word. So what is w here? We only have x as a w. So then xw is in summation. So multiply x with w means x with x. That will be in summation. So then this is w. Multiply this with x. So this will be in summation. So you see that this way you can generate your summation there. If you are interested to write the recursive definition for the clean star, so So you are saying that, okay, so summation clean star is equal to rule 1, lambda is in clean star and w is any word in clean star, then xw is in clean star. So we only have lambda here, so multiply x with lambda, it will be x, multiply x with again this lambda, this x, so this will be 2x. So now this is my w. All these are, so w is a variable, all possible words which you already generated in your language in x in summation star, this is w. So you can use lambda as w, you can use x as w, you can use xx as w, and you are saying that all these are part of my language and job is done. Then you are saying odd language. Uh, if this is your odd language and S odd, so now you are saying rule 1, X is in my this language, so S odd. X base case is X is there. So if W is any word, what is W? W is at this time X in my S odd language, then XXW is in odd. So always multiply 2x. So it will be 3x, then 5x. Okay, so this will be w, so multiply this with 2, concatenate with 2x, so 5x, and so on. So this way you will have all odd numbers of x's in your language. So this way you can generate odd, even, summation, star it, and assume that with all these definitions you must have rule 3, that there is no other rule than rule 1 and 2. So this is basically something which is there. Okay. um, Am I going very fast? I'll finish this very quickly, this slide. Do you guys understand this? Lion, do you understand this?
I understand.
Excellent. And Riley, are you here? Do you understand this?
Yep, so far so good.
Excellent. Okay, so I'm trying to remember your names. So now we have this slide. It says positive. So rule 1 is all positive numbers. So now rule 2 says if w is any word in positive, then okay, so basically we are saying that we will have all positive words which do not start with 0. So we will not have any word which is 0 1 or 0 2 or 0 3, something like that, and 0 is also not part of this language. Now this is, that's why if you see this, our rule 1, we are saying okay, we have a language which is called positive and we want to generate the word, and we are saying rule 1, 1 to 9 are there, so 1 2 are there in my language. So rule 2, if w is any word in positive, so how many w's we have 9 w's here, 1 as a w, you can use 2 as a w, 3 4 5 6 7 8 9, any word which is in positive will be used as w. W is a variable. So then concatenate w with 0 means I use 1 as w and concatenate with 0, I got 10. W, I use 1 as again and concatenate with 1, 11, 12. So this way I can generate any words of this language which is in positive, but it will not have any word which start from 0. So you will not find 0 1, 0 2, 0 3, or only 0 there. So this is the definition of this language. Okay. So now let's see clean star already. So I already explained that in the previous slide about the star. So it says rule 1, S is a language. All word of S are in S star. So lambda is also part of there. So then you are saying if X and Y in S star, so then their concatenation X, Y is also in S star. So it is exactly what we did here with the star. Okay. So we already did this. The same thing in more nice way. And now let's see the arithmetic expression. So we want to figure out how we write define the recursive definition to generate the arithmetic expressions. So we are saying that summation is equal to this is our, so when we say summation, so it means that our basic building block. So all this will be summation. Okay, so it means that when you want to define the arithmetic expression, these things will be there. And then you are saying that rule one, any number positive, negative, or zero are in arithmetic expression. Rule 2. If x is in arithmetic expression, the following words are also in arithmetic expressions. So these words are also in arithmetic expressions. Okay. Then we are saying rule 3. If x and y are in arithmetic expressions, then following words are also in arithmetic expressions. You can add two words, you can subtract, multiply, divide, or exponent. Okay, so all these are valid arithmetic expressions. And rule 3, rule 4, there is no other rule than rule 1, 2, and 3 to generate the arithmetic expressions. Okay, and this is your summation. So now let's see, we have this terminal, this term here, this equation here, and we want to see that whether this is valid arithmetic expression or not. So exactly the way you solve the polynomial, you do the same thing. So first you pick this thing, that 2 is, so first we follow 2, we are saying 2 is there. So by using rule number 1, any number positive, negative, or 0 are in arithmetic expression. And then we pick the same rule for rule 1 for 4, and then we are saying that x and plus y is also an arithmetic expression. If x and y are two numbers which are already there in your arithmetic expression, you can add them. This will still be the arithmetic expression. So 2 plus 4. And then you are saying that whatever the term you have, you can put the parentheses around that. It will still be in arithmetic expression, and you put the parentheses around that because this is now your x. We consider this as one term, and exactly this way you generate 2 plus 4. And the same thing you will use for 9 plus 9 minus 3, and then you add this thing, and then you add uh, this whole thing you generate, and then 2 plus 8 and this thing, and finally minus 1, you add that. So gradually you can increase that, so that this is idea now behind that, how to generate this thing. So it is exactly the way I did this polynomial, exactly the same steps you will follow, and by these rules you can generate this arithmetic expression, and you can say that yes, this is part of the language, this is valid arithmetic expression. And we can prove that by using all those rules. And we will state that we get this step by rule 1, we get this step by this rule, whatever the rule we use. Okay. So the logic is that the fancy thing is how you design these rules. So this is something very important. So you should understand. So now this requires your basic knowledge. You should understand what is arithmetic expressions, what is odd language, what is even language, what are prime numbers. And if you know all this information, and then it will be very easy for you to generate the rules. Okay, that's the idea behind that. So this is one theorem here. It says that uh, an arithmetic expression cannot contain the character dollar sign. So how we prove that? So it says that dollar sign is not part of arithmetic expression. So now you can prove this by looking at all the rules. If you see that in your summation, you do not have anywhere dollar sign here. So in summation, it is not there. Rule 1 does not talk about, or rule 2 does not talk about dollar sign here. Rule 3 does not talk about dollar sign here. So by looking and investigating all the rules, you can say that it is not part of the arithmetic expression. The character is not part of any number, so it cannot be introduced in arithmetic expression by rule 1. And then the same thing if the character string s does not contain the character dollar. So because the next rules we generate from the rule 1. So if it is not there in rule 1, it cannot be, you cannot do that in rule 2 or rule 3. So then neither do the strings x or minus x, so it cannot be introduced into AE by rule 2. And if it is not there, so then x or y are not there, so then it will not be part of this rule 3 also. So this shows that this is good, that this theorem that arithmetic expression cannot contain the dollar sign. So we prove this. Okay. Just by investigating the summation and all the rules, that is it possible that you can at any stage get dollar sign there? If it is not, so it is not. So there is no word in AE that begins or ends with the symbol slash. So now this is tricky a little bit. If you see that slash is part of your arithmetic expression, okay? Slash is part of your arithmetic expression. But what we are saying, that arithmetic expression will not start or end with slash. Now this is good. So now if you see this, yes, it is part of the summation, but rule 1, according to rule 1, slash is not there. According to rule 2, you cannot put slash anywhere here. According to rule 3, you can put slash in between x and y, but you cannot put slash before x or after y. So we do not have something like this. Okay, so that's the reason that we can prove that what this theorem is right. You cannot begin an arithmetic expression by investigating all these rules with slash. Okay? So this is the way you can prove that. And then you are saying formulas of propositional logic. So rule 1, all. So how we generate the formulas? Can we define the recursive definition of the formulas? So we need to see this. So we are saying that if you have uh, all Latin letters are in formulas, the Greek letters and the Latin letters, all these letters are in formulas. This is my rule 1. So rule 2, if P is in formula, so P is a variable, all letters which you put there in your formula, that will be the candidate of P. So then you can put parentheses around that, or the not sign P are also in formulas. And if P and Q are in formulas, so then P tends to Q is also in formula. And the rule 4, there is no other rule than rule 1, 2, and 3. So I mean, thing is that so now you need to understand how we generate the formulas. You should have the basic knowledge of that particular thing, how we generate that, what does it composed of, what should be the base case. You should understand, if I ask you write the recursive rule for the factorial, what is factorial, what is science behind that, what is math behind that, how you generate the terms of the factorial. If you know that, so then it will be easy for you to understand how to write the recursive rule of for that particular language. So that's the idea behind that. And whenever you generate, do not forget to follow the template of the recursive definition. And that template is number 1 rule, base case. Number 2 rule, derive rules to generate words, future words. Number 3, no other rule. Then 1 and 2. So this is the template. So if you follow this template, so you are good. This is just some kind of I just write in very short way. So these are the three rules basically. But you may have more than one base case. You may have more than one rules. But the it should match with the template. And here I think that we are done. Any question, guys? We done this chapter.
No.
Okay, I think that we are good. Do you want to continue, or you think that we should go slow and this is enough for today?
I'm fine with going slow and this being enough.
Okay, okay, that's great. So let's stop here then, and you guys, yes, but I mean the next chapter 4 is a very long chapter, so I think that we are not able to finish in one day, but we will try. Uh, Yes, yes, yes. So, Quinton, if you have any question, please do not struggle by yourself. You can use office hours. You can send me email. I suggest all of you, please do not struggle by yourself. I should be your first source of information. Please use office hours and come online. You know that how to connect with office hours on the main page where it says the office hours. I make that as a link. You click on that, it will open another WebEx meeting. I During the office hours, I always in the meeting, I create the meeting and I will be there. I will wait for you for 1 hour, whether anybody come or not. I will always be there. So, and beside, if that time does not suits you, might be you have another class, send me an email, or we can do meeting very quickly on WebEx any other time. So of you which suits you. So we can do that way also. Okay. So, but my point is, please do not struggle yourself. I should be ask me, use the resources. Ask me. I should be your uh, first point of information and the source of information. Okay, guys, thank you very much. I know it's hard to stay live in this course, and it is hard to wake up, and it is not possible without you guys. Thank you very much. Stay safe inside, and let me stop recording.
Thank you, Professor.
Thank you very much.